All right, I have started the recording.
Okay, hello, welcome back to the Kokkos Lectures. Today we are gonna hit Kokkos kernels finally, and we'll talk a bit about the math library and the math kernels. But before we go there, in this last lecture of our series, we will go to a little recap. Obviously, as always, we have all our online resources available. The slides are already up in the repository, so if you go to the Kokkos Lecture Series wiki and you click there on slides, you can find these slides online there right now. As always, join our Slack channel even after the series is over. That's a place where you can ask all your questions, and you will also find the Kokkos kernels folks there. So if you have questions for the Kokkos kernels folks and how to use the math library, etc., after this lecture, please come there. So this is the last one in our series. We, this is the 8th one. We discussed a lot of things in the last 2 months. We went through the entire Kokkos programming model. We learned how to do parallel dispatches. We talked about data structures. We talked about, how to manage heterogeneous machines. We talked about tasking and streams and SIMD, etc. We talked about interoperability with MPI and PGAS and Python and Fortran. And last week, we talked about tools. We talked about profiling, tuning, and debugging. Just as a little recap on that, so we introduced the difference between the instrumentation interface Kokkos P and the tools that leverage that interface. One important thing about it, I hope you all got away from it, is that this interface is always there, even in your release build. So you can use the Kokkos tools with your executables without recompiling. You don't have to turn on any special options or something like that. It's always there. It's zero overhead if you do not load the tool. And you do load the tool by setting the Kokkos profile library environment variable. And that can inject things into your code which uses the instrumentation layer. You can actually also compile tools now into your executable and set callbacks explicitly in the code. We talked about the Kokkos connector tools and how we leverage our instrumentation interface to provide information to third-party tools such as Insight Systems and vTune, etc. We talked a bit about how there's a growing list of tools which support Kokkos natively, like for example Tau and HPC Toolkit, which on their own will figure out that, oh, you are actually using you're running a Kokkos code, and let me grab all that information you put in there. And we talked about how this is the real reason why we force you to name your allocations and why we really strongly encourage you to put names on all of your kernels. We talked a bit about the Kokkos tuning hooks, the auto-tuning hooks, and how that enables you to get more performance portability out of your codes. And we talked about how you can implement your own tools and how it's actually relatively straightforward to do that by just implementing couple of C callback functions and only the ones you actually want. We talked there a bit about how you can use that to write like throwaway debugging tools, for example. And then last but not least, we talked about static analysis, how you can have now with the Kokkos LLVM sub-project, how you can get semantic checks for making Kokkos mistakes which aren't strictly speaking C++ errors, and how you can integrate that into your editors, and how it allows you to catch errors before they bite you later on some specific machines. So before we now come to the Kokkos kernels part, I will walk you through the exercise. We had an exercise which was, where you were supposed to find a performance problem in a version of MiniMD, which I crippled. So if you can see my console now, I'm in the Kokkos tutorials exercises in the tools MiniMD exercise. As always, I have Kokkos installed or Kokkos cloned in the Kokkos directory. And I also have the tools downloaded in Kokkos Tools. So before we go into the exercise itself, we need to make sure that the tools are actually compiled. So we'll just go there. And I said we are following the kind of standard procedure of running tools. The main tools we're going to use there are the profiling ones. We'll start with a simple kernel timer. So I'm just going to type make here. I already had that built. You see the KP kernel timer SO, that is the shared library, and the KP reader. Just to show you, these make files are super simple. They really just built with G++ shared library. There's nothing special happening here. Then the other tools we're going to use are the memory usage. That's already built, and the memory events. And maybe I'll show you also the space-time stack. So, okay, all of these guys are built. Now I'm going back to the Kokkos tutorials, to the tools, exercises, tools, mini-MD. Okay. Why does that not work? Because I forgot the CD. Okay. And now let's first build this. The thing is set up to build OpenMP by default, but let's actually build for CUDA. So I change the device here. I also need to change my compiler to use NVCC wrapper. That builds this library. It's actually using here MPI stubs library. So the build right now is set up to just be non-MPI, but it has to, kind of get the, fake MPI calls in there. You can also build this actually for MPI and then run on multiple ranks, but the performance problem shows up, quite significant on a single rank. So let me run this first. I'm running a relatively small system. The -s essentially tells you what is the linear dimension of like a crystalline, structure. So it's doing a 20 by 20 by 20, problem setup, which ends up with 32,000 atoms because there's like 4 atoms per unit cell. And now it's running this thing. And it takes quite a while, right? So it took like here 12 seconds to run this. One thing we can look at is the performance or performance per thread, which is kind of like the performance per MPI rank here, because we are running non-threaded on the CPU. And you see it has like here 267,000. This is a performance number. It actually is how many atoms do you advance by a time step per second. To just get a feeling for what it should be, there is actually reference output here for like a 30K Leonard-Jones problem, which is what the default here is running. And if you look at the bottom here, this one was running 19 million, right? And this was actually a run with 16 MPI ranks using just the serial backend, right? So this was just running 16 cores. And the cores are actually way slower than what the Volta GPU should do. The Volta GPU in a non-crippled version for this kind of code should actually run roughly around 100 million or so. So we lost about a factor of 500 or so in performance here. So now the question is, how do we find out what's going on? As I said, we can just set environment variables to load tools. And in the lecture last time, we said that you start with something really simple. You just get an overview of what is going on. So we'll start with profiling simple kernel timer. Go. So we set that environment variable. And if we now rerun the same thing without changing anything else, it actually tells you here that the Kokkos P loaded something. And at the end of it, it will hopefully tell us that it did some output. Indeed, it did. There is now a file where it wrote the kernel timing to. This file is actually a binary file, so we're gonna run reader for that thing, which was built in the same directory. 6523 that. Okay, here we go. So what this does is at the end, you know, the bottom line, we ran 13 seconds. Only 2 of those seconds were spent actually inside of a Kokkos kernel. Note the lower k here. So lower k means that it's not a morph library, but just a, you know, parallel dispatch. And 11 seconds outside of that, right, in serial host code. So that's already a big problem, right? The other interesting thing is we ran 193,000 kernels. That is pretty bad. If we scroll all the way up, we see here the force compute, you know, at about 0.01 seconds, and we spent over 2 seconds in view initialization. And if we look at that number here, we had 192,000 calls to view initialization. This is essentially the call kernel which sets the values of a view to 0 when you allocate a new view. But let's look at some other tools first. I mean, though that was already a pretty good hint. Let's run the memory usage thing. So I think it's memory usage kp memory usage.so. Okay, it's running. And let's see if we got output. We actually did get output. Oh, I didn't delete some early output. Here these files. So essentially what you see here is you get output per, you know, this is the host name, then the process ID, and you get output for memory space usage on a per memory space, you know, basis. So let's look at the host one first. And what you see here in the host one is that you get 4 columns. You get the time, the size, as the current size at the time, the high watermark up to that point, and the high water process. The high water process is essentially what we get from our usage. So it includes other stuff, you know, which isn't Kokkos. Well, the first ones are only Kokkos numbers. And what you see here is, you know, we grow a bit and then we go down a bit. In total, every entry here is essentially, if it goes a bit down, right, it's a deallocation. If it goes up a bit, you know, it's an allocation. So there's 94 host allocations or deallocations happening. Also technically there's, you know, 47 allocations and 47 deallocations, hopefully. If we look at the CUDA one, that one is a bit more interesting because it's really long. Right, 623,000 entries. And if you look at that, you know, there isn't all that much happening, right? This is here, like, it's going down here. This is the deallocation phase, and it's going down by you know, way less than a kilobyte per entry, right? So, okay, we can get a bit more information out of this if we run the memory events thing. Memory events kp memory events.so. Let's run that for a second. This will actually generate the same memory usage files, but it will add one more file at the end.
Christian, we didn't get the message that the library was loaded.
What? No, it's fine. This tool didn't print anything. It's the tool's task to print whether it was loaded or not. So this tool decided not to print anything, so you don't get an output. You will get an output if you mess up the library. So if there is actually no library to be loaded there at the place, as if a file path is wrong, then it will tell you so. Okay. Here's our memory events, and you see now more output, right? You see now a time, the pointer, the size, the memory space, whether it's allocating or deallocating. You see that here, and the name of the allocation. And at the beginning, you know, all kinds of normal stuff happens here. This is, you know, where it allocates and deallocates. It's kind of a setup phase for the force-like parameters, etc. And then if we go a bit down, right, now weird stuff happens. I'm getting endless entries for this neighbor's VOV of only 312 bytes. And it's one thing to know about this is Kokkos actually reserves 128 bytes for like an allocation header. So a good chunk of that is actually not the actual allocation. Let's go a couple lines further, like, I don't know, maybe 80,000 lines. Okay, what you see here is now, we are now in a phase of a program where it deallocates something and then allocates something, right, with the same name. And funnily enough, it allocates deallocates something, and then it allocates something again right away of the same size. So sometimes not even the actual pointer address is changing, right? And this is obviously a problem. This is, you know, something which hopefully, you know, shouldn't necessarily happen. So if we, let me go back. Let's copy this guy here. So what we should do is we should grep for this guy. And where we see, it shows up in neighbor CPP at line 137. So let's open that guy. 137, here we go. That's the offending allocation and deallocation. So why is that happening? We can look a little back. It's doing the neighbor list build here. It essentially first figures out how many neighbors does every particle have in this particle code. And then it reallocates, it resizes all the neighbor lists, right? Before it fills the neighbor list. And what I'm doing here is I'm using actually a view of views, right? So if you look at that, I'm resizing the, here this neighbor's view of view. And for every particle, I'm assigning a new view, you know, with the length of how many neighbors does that particular particle have. But there's multiple problems multiple things I did wrong here. One thing I did wrong is I reassigned that without checking how large is the old view. So even if the old view is exactly the same size, right? Nothing changed in terms of numbers of neighbors. It will assign a new view, which means the old one will deallocate and the new one will be allocated, right? That is a problem. And the second problem is I didn't tell it not to initialize the thing to 0. In the neighbor fill phase, I will overwrite every one of these values. So by not telling it to not initialize, right, it will actually launch a kernel for every one of these tiny little views to the GPU. And that is where our 190,000 kernel launches come from. And what you saw here is that we got multiple hints at that, right? The first hint was actually when we looked at the output with the KP reader, the view initialization here of the neighbor's VOV, it actually tells you which view it is. And the fact that we did 192,000 of these kernels is already a good hint, you know, that that is the problem. And then you saw the allocation deallocation thing. And this is actually a typical thing which happens a lot in applications, right? That you do somewhere temporary allocations, or you messed up in terms of, you know, reallocating something you shouldn't reallocate all the time. And this kind of tools, you know, can help you find these kind of simple, typical errors very fast. Okay, that was the walkthrough through the exercise. With that, I'm gonna stop sharing, and Siva is gonna take over and give you an introduction into Kokkos kernels.
All right, thanks, Christian. I'm Siva Rajamanikam. Thank you, everybody, for attending this lecture series. Today's discussion is going to be about Kokkos kernels. This is a math library that is for sparse and dense linear algebra kernels and graph kernels. there is a large team that works on it. All of them are listed. And there are other contributors who used to work in Kokkos kernels who are not there anymore. And you will hear some of these folks speak today as well. I'll give an overview of Kokkos kernels, and then different folks will give will describe individual aspects of Kokkos kernels. Okay.
I click on it and then try again.
Yeah, give me 1 second. Okay, hopefully this works this time. No, it doesn't work. I'm going to go out of the full screen mode. And just keep it and the slideshow mode, and hopefully that works. Okay. So here is Kokkos kernels. It is part of the Kokkos ecosystem. You've been listening to lectures on the Kokkos ecosystem. This is the 9th one. So you probably have seen this figure before. Kokkos core is the foundation for this entire ecosystem. This is the programming model that gives you the Kokkos views and data structures and everything that you've been hearing about. Kokkos tools on the left-hand side is what you are going to, what you heard about just now, Christian talked about, and what you heard about in the last lecture. Kokkos support is a project, not a product. It is a project that helps us do these kind of tutorials, allow us to do boot camps, work with applications. And this last lecture is on the component that is on the top of Kokkos core, which is Kokkos kernels. We have linear algebra kernels and graph kernels. And so this basically completes the ecosystem. If you are an application, you are starting to write parallel code. First, you will start with how to parallelize an individual kernel, how to get good performance out of it using Kokkos tools. Can I debug this kernel? Everything is going well in my kernel. Now you want to optimize even further. You are looking for optimized libraries for individual kernels like sparse matrix vector multiplication, sparse matrix multiplication, graph algorithm to do a particular distance one coloring or something. Is there a library available, or should I code that each one of those kernels myself? If I want to do a matrix multiplication, do I have to do that myself, or is there a library available? And in the Kokkos ecosystem, Kokkos kernels basically solves that problem, where we write these library to give you the common kernels that you will use. And Kokkos kernels, like rest of Kokkos, is available in Trullinos, and it is also available outside Trullinos. So, and it has a large user base within the Trullinos software framework at San Diego. Okay. And then you don't need to do that. You can just get the Kokkos ecosystem by itself, and the application can directly talk to the Kokkos ecosystem and Kokkos kernels straight out without using Trullion. Okay. Now let me talk about the focus of Kokkos kernels at a very high level. Number one, we want to deliver portable linear algebra and graph kernels, like I said. But do we want to do any linear algebra or graph kernel? We don't have the manpower to do this. We focus on kernels that are the most performance critical for an application, and that is generalizable across multiple applications, so that we are able to serve a broader user base. And that has been our focus for a long time. So if there is it is a common kernel across multiple applications and it is performance critical, we are happy to implement it, develop algorithms for it, and support it in different platforms. That's number one. The second is to have this robust ecosystem of within Kokkos, so that if there is a Kokkos user, you have Kokkos views, and you want to call matrix multiply, you want to call it gem, you want to call it triangular solve, you have an option to call it right away. You don't want to hand roll each one of these kernels. And do this in a production level software capability, so that we, as Kokkos core, as you've been hearing about in Kokkos core, Kokkos kernels is also tested across several different configurations, architectures, compilers, and programming models. We test for multiple different data types, and the integration and the release is exactly with Kokkos. So if there is a Kokkos version 3.1, there is a Kokkos kernels version 3.1 that matches Kokkos core version 3.1. Okay, and the support we do we follow exactly the Kokkos model. We use GitHub issues. We follow the same tutorials, and we are on Slack so that you can reach us in Slack as well. Now the other focus is these kernels essentially are highly optimized, but they almost become like a reference implementation for what our applications need. And if you see that, then we write these first optimized implementation. We work with the application, find out the kernel, come up with an optimized implementation. We write that, but then it becomes a reference implementation. We work with several vendors. I'll give you a set of examples in a minute. And we work with these vendors to get even better implementations in their libraries. And once there is a vendor implementation that is available, we just pass through to that, so that the user you don't have to switch between Kokkos kernels and the vendor implementation. You can just keep calling Kokkos kernels. If we figure out for a particular problem size in a particular architecture, there is a vendor implementation that is better, we would just call the vendor implementation. And we still maintain the other optimized implementation where the optimized implementations are not available. We maintain our own implementations as well. And most of these algorithms that we have developed in Kokkos kernels is published for the community, so anyone can take it and use it as well. The next thing is we actively partner with applications. And this is not just for finding out what the kernels are. This is basically finding out what are the right interfaces, what are the use cases that the applications need. And I want to highlight a few of them. And some of these are not even supported by vendor libraries now. For example, ECP applications in particular wanted to have these team-level dense linear algebra, team-level sparse linear algebra, and data structures and utilities at the team level. What do I mean by the team level? You have a parallel for that you are working for different set of rows, different set of elements, and then you want to call a linear algebra kernel or a data structure inside the parallel for. You want to do a matrix multiply, you want to do sorting within that parallel for, and this is not well optimized. But this was one of the important application requirement, and we support that in Kokkos kernels. And we are, like I said before, we are working with vendors so that they support it in the future as well. And then fused kernels. Again, there are these kernels that are critical for performance, but not for one application or one use case. The use case I would point out is multigrid, which is common across several applications. And if there are fused kernels needed for those particular uses, then we provide fused kernels in Kokkos kernels as well. And finally, a lot of improvements in linear algebra is through having good interfaces, good and clean interfaces. And so, for example, we use this symbolic and numeric separation in the interface design so that we reuse a lot of our information in different kernels multiple times, so that to optimize for performance for solvers or applications above Kokkos kernels. Okay. I'm going to highlight a few collaborations we have, both in terms of vendors and in terms of applications. Let me start with the vendors. In terms of vendors, we work with almost all the vendors that are in this space for providing HPC hardware for CSE applications. NVIDIA, for example, we have bi-weekly meetings with them in different work streams in math libraries and in terms of hardware, compilers, machine learning in different work streams. And a lot of the implementations in Kokkos kernels, like SPGEM, GEM, and solvers have become good collaboration points for NVIDIA's libraries as well. In terms of ARM, again, we work with them very closely, and these linear algebra kernels and batch linear algebra kernels have also become part of the ARM performance libraries. Okay. In terms of AMD and Intel, as you might have heard from the previous Kokkos lectures, we have started interactions with them to have a Kokkos backend in Intel hardware and in AMD hardware. And once the Kokkos backend is ready, the first step, the next logical step is to have Kokkos kernels compiled and evaluate the performance, right? And that becomes our second logical step, so that every kernel in this ecosystem is ready to be used by the applications on that particular hardware. In terms of collaboration with applications, we have active collaboration with several ECP applications and co-design centers. I would like to point out the applications here, but there are a lot of other co-design centers as well that use Kokkos kernels. Number one, there is Spark, which is a hypersonic, unsteady, hybrid unstructured structured finite volume code. This code uses this team level linear algebra kernels that I just mentioned. They wanted something very specific in terms of calling dense linear algebra kernels within a Kokkos parallel form. Okay, and the Empire is this finite element pick and multi-fluid plasma simulation code. This code uses a huge software stack that starts from multi-grid solvers and all the way to some very small, very low-level kernels, and it uses Kokkos kernels and of course Kokkos core along with it. And most of the work here is for linear algebra, sparse linear algebra kernels and dense linear algebra kernels to make the solvers fast. Okay. And the XFWind is the wind simulation code from Sandia and NREL, and this particular code uses scalable solvers from Trulinos. And the focus here is to make the solvers really fast using sparse linear algebra kernels. And then we also have QMC pack. We've started discussions with QMC pack for team level linear algebra, primarily BLAS and LA pack. And this is an ongoing discussion. Okay. So that is an overview of the software and what is our focus for. What are our collaborations? Here is a overview of what we are going to talk about today. And different folks are going to cover different areas. We would first start with dense linear algebra kernels with BLAS and batched BLAS. Then we would cover sparse linear algebra and graph kernels as a second and the third. And then finally, we will finish with sparse solvers and build system. So that is the agenda for today. We have 5 different topics. So I'll stop here and we would start with BLAS and batched BLAS next.
I need to unmute first. The button is disappear. So can you see my screen?
We can.
Yes.
Okay, so my name is Kyung-Ju Kim, and I'm going to give you a presentation of BLAS and LAPACK interface in the Kokkos kernels. So for your information, the BLAS means the basic linear algebra subroutines, and LAPACK is the linear algebra package. And these are developed a long time ago in first with Fortran, and it is well adapted in the scientific computing community. And usually the Intel or Kublas or other the business vendors provide the optimized version of this code. Because this is written in the fortran, usually it is written in the specific data type, kind of plot, double, and complex plot, and complex double. And now we are using the C++, and we can kind of provide a high-level abstraction of this interface. And there is some external effort to providing this high-level abstraction, such as the eigen or the boost library provides the mu-blast. Then what the Kokkos kernel is unique from the other high-level abstraction. The first, because the Kokkos kernels lives in the Kokkos ecosystem, it has the natural extension to the heterogeneous computing platforms. And also we have the template-based implementation. So our native implementation can support the user-defined data type. In the Trillinos, we can use the automatic differentiation type or ensemble type or the UQ analysis, and CMD type or the embedded vectorization. And also, this is the most important part, I think, that we can provide some customized performance solution working with the application people. Because the other vendor library or the other high-level wrapper interface just provide some interface, but we are interact with the application people and providing some edge case solution. So this is some example we provide to the applications with the algorithm specialization. So when we do the Krylov solver, we need to do the orthogonalization, the Krylov vectors, and the shape is usually the long and skinny. And for this case, we use the matrix multiplication that is called the gem. And this particular operation does not perform well on the cuBLAS because the matrix shape is skinny and long, but usually cuBLAS or vendor library is performed very well on the relatively large matrix. So we provide the dot-based gem, which just changes the internal algorithm using the dot product inside. And another example is the compact batched BLAS, as Siva mentioned before. The CFD solver Spark want to solve the many square problems, but the block size is kind of 3, 5, 7. None of them is power of 2. So it is very difficult to utilize the wide vector lengths. So we pack the block matrices in interleaved fashion, and then we solve those pack of problems simultaneously using the vector intrinsics. So the code is trivially vectorized for this case. This can boost the application performance very well. Another example is we have some sort of the extended BLAS1 interface. If you are familiar with some BLAS level 1 function, this AXPBY standard represents this portion of the code. So it just scale and add 2 vectors. And in the Trillinos, the iterated solver values require this certain functionality, and then we cover that functionality providing this interface. So takeaway message is the Kokkos kernels interact with the applications, and we can provide some custom performance solution for their needs. So now we are going to talk about the specific BLAS and LAPACK interface using Kokkos kernel. And we are using the same example you guys already have before. And this is the inner product example. So simply we do matrix multiplication here and then performing the dot product. Using the Kokkos notation, this can be expressed in this way. And this is the single parallel 4, and it is parallelized over the dimension of n, which is the number of the rows of A. And if you see here, we are kind of sequentially summing up the value here. So that means if this m is large, then we have the large of the sequential portion. This code cannot work very well. And if we have the n is small, then we cannot we cannot exploit the entire GPU very well because we don't have the many parallelism there. So we can divide this operation into 2. One is the matrix vector multiplication. In the BLAS standard, we call GEMB. And then second one is the dot product. We just give this the MATLAB notation here. MATLAB notation here. So if we code this, even though we use Kokkos, if we just want to call the different BLAS function on the different architecture, that means you need to write separate the routine for the different architecture. So if you use the Kokkos kernels, you can use the single Kokkos interface, and then internally we can kind of interface to the kuBLAS or MKL if they are available. And if you give the weird strided data layout matrix, then we can use our native implementation. So this is the detail of the Kokkos BLAS interface. And this mode is included the transpose of the matrix A. And A is provided as the Kokkos view. So it can be layout right, layout left, or layout strided if this is the sub-viewed from another multidimensional array. And same thing happen in the X. So in terms of the dot product, we have the two interfaces. The one is we want the result from the host directly. Because we want the result from the host, it needs to finish the computation before it actually returns the data value. So this interface calls the fence inside. On the other hand, we can give the result as a kind of a value or value of the view. So this is the rank 0 view, this is the scalar view, so it can live on the device. In this case, the result may not be available right after we call this. And then we need to fence if we want to retrieve the data from the R view. So this is the Kokkos kernels version, and we just created a temporary vector here and then called the GenB, and then we want the result from the host, so we just call the dot product. And this is the previous implementation. Because we use the two BLAS functions, and also optionally it can interface the optimized vendor library, so it can perform very well. And for the certain problem size, we can kind of call the different code internally. So if the GenB has some kind of different weird shape, then we can kind of customize the algorithm internally. And on the other hand, here, we explore single level parallelism. So our parallelism is limited by this number of n, and we have the sequential portion here. So sometimes it works very well because we just launched the one parallel 4. Here we launched the 2 parallel 4. So, but this is not really portable for the arbitrary size of the matrices. And we can find this exercise from the exercise to the repo, and then you just find the inner product. So this is the summary of the BLAS and LAPACK. We provided a single interface for the heterogeneous computing platforms, and optionally we can provide the optimized vendor interface, and we provide the specialization of the algorithm where application needed. And native implementation can support the user-provided data type and also stride data layout that is not supported from the vendor libraries. So now we are talking about the batched BLAS and LAPACK. So what is the batched BLAS and LAPACK? It's very simple. We want to put the BLAS and LAPACK inside of the parallel 4. This is really simple if we just think about the host architecture. But when we go to the GPU architecture, it's not a trivial question. For example, in the Kokkos execution policy, we already have the 2 different execution policy. One is the flat parallelism with the range policy. Another one is the hierarchical parallelism provided from the team policy. So we need some kind of matching interface to this hierarchical parallelism. So we suggest to provide the 3 different interfaces. One is the serial interface. This serial interface can be used with the range policy, and single thread is working on this particular function. And this serial interface also can be used inside of the team parallelism if this is placed in the most inner loop of the next parallel 4. So in this particular case, we have the parallel for over the team thread range, parallel for over the thread vector range. So we now make sure the single thread is going to work on this serial do something. So in the next, we have the team vector interface. So as this name specifies, it uses the parallel for inside with the team thread range and thread vector range. And this requires a team member as a thread communicator in the interface. So we just call the team policy, and it is safe to call the whatever called the team vector do something here. The last one is the team interface. Team interface is very kind of a special interface. This is required if the vector parallelism expressed inside of the data type, like the SIMD or ensemble type. They can utilize the vector parallelism internally, so we cannot include that in the interface. So for this particular example, we have a team policy, and then we do Kokkos batch the team do something, and it means that our data type may use internally the vector parallelism. So if the data type does not use the vector parallelism on the GPU, we can kind of flip the loop. So we can put this thread vector range outside and then put the team parallelism inside. This is some advanced use case. So now we are giving some example. So consider a block Jacobi preconditioner. And this is simple, like we want to invert the large of the block, small block matrices. So for the notation that we are going to use in the next slide, we are using the view type AS, and then we are using this scratch space. Scratch spaces comes from either from the GPU programmable cache, or it can come from the global DRAM memory. So using the Kokkos kernels, we are launching the single parallel for. The inverting the block matrix A is, we first need to factorize the matrix A into the LU. So L is the log triangular vector, U is the upper triangular vector. Because we want to invert this A and then store into the A inverse into the original matrix. So we need some copy, temporal matrix copy, and that is copied to the T. And we put the identity of the A, and then we perform the lower triangular solve and upper triangular solve. It will invert this matrix A and then store the inverse into A. So as you see here, in the Kokkos kernels, multiple BLAS and LAPACK functions are kind of fused in a single parallel for. In this way, we can use the temporal locality. And also, we can use the local cache memory as a scratch space. However, the team size, I mean, when we create this team policy, we need to define the number of leagues and number of teams and the number of vectors. So this team size is supposed to be tuned. And there are several algorithms inside. And some kernels work very well, but some kernels may not have such parallelism. They can utilize the entire team of these threads. So if this team policy is poorly tuned, then performance can be poor. I'm going to demonstrate this in the next using the example. So if you use the Bender library usually do this way, like the batch parallel LU. So we are computing the LU factorization of the entire matrices and then copy and then set the identity matrix, and we do lower triangular solve, upper triangular solve. But each function can be highly optimized because we do one operation at a time. So in the sequence of the batch operation, this workflow may not be optimal. So if you want some kind of optimized version of the invert the matrix, you need to request the vendors. I need this function, please provide this. And if you are lucky, maybe you can find this kind of function and you don't have to do the kind of fusing or something like this, because this is probably most optimal way to use the Bender library. So now that we have the two namespaces, the one is the Kokkos BLAS, and this Kokkos BLAS namespace uses the device level function, and it uses the entire device. And usually because when we use this on the GPU, it's non-blocking, it's by default. And then if you request a result on the host, then it will finish the computation, and because it incurred the data transfers. Another one is the Kokkos batched interface. This is a more kind of a functor level interface. It has the layered interface with the serial, team, and team and vector. And this is supposed to be used inside of the user's parallel for. So this is the team gem operation. And team gem is we want to compute the matrix multiplication in a parallel for. So the P is the number of problems, and M and K is the matrix dimension. So if you do this by yourself, you probably do this way. You're going to put the team parallelism outside, and you need to decide this team size, and then you create the next parallel for, and I want to use the 2D parallelism, so we give the ij index, and then we decode this index I and j here and update the cij individually. In the Kokkos batched routine, you can use this way. We get the matrix from the three-dimensional, multi-dimensional array of A, B, C, and then call this the team gem inside. So this matrix multiplication is simple. Maybe you want to do yourself, but if you write the more complicated numeric kernels, and it's probably better to decompose the operation as kind of a blast operation, and you can write your own batched routine, which can be applicable to more complicated kernels. So this is another example of the block Jacobi that I explained before. So the objective is we want to compare what's the better about writing all the small dense operation in a single kernel, or we just write the batch kernel run the non-fused way. And you can find this example here, and it's you just compile, and then you can run the script. One is the run different team size. The other one is running the MBprop and showing the profiling result. So this is the summary of the output. So this is the team size. We test with auto, and then team size equals 32 and 64, 96. And this is the non-fused version. That means that we're going to call this the for parallel for with the LU, set copy, identity, and triangular solve lower, triangular solve upper. And we run the for parallel for independently. And the other one is the fused kernel. We launch the single kernel, and then we put the functor level interface inside of the single parallel for. And in this test, we are solving the 16K the problems, and each problem is the 5 by blank matrices. Then we noticeably see the team size is 32 working best. And then why? If we just simply assume all 25 entries of the block is updated independently, and 25 threads is the maximum thread we want to use. And if we put the 96 thread, and pretty much about the 70 threads are going to be idle. So it makes sense. Using the 32 is probably best. And also, if we compare these two numbers, non-fused and fused, when we fuse the operation, we use the temporal localities used, so we get the better performance. Now this is our kind of suspect, and we need to check this using MBprop. So the first comparison is what's the difference between auto and then team size 32. We manually set this team size 32, speculating this algorithm. The other one is the comparison to fused version versus the non-fused version. Why we have such different performance characteristic here? So in the first case, we are using the same code but different team size. And Kokkos Auto set the team size equal 96. And usually when you use the auto, it set the team size that maximize the occupancy. And if you look at the occupancy here, it's higher than when we use the 32 team size. But if you just compare this, the global load throughput, and we have the higher load throughput. So this difference is roughly 1.7, and it's directly correlated with the performance difference. Another comparison is we are using the same code, but the first case, the non-fused version. So we are running this kind of kernel 4 times. I just grabbed the one best performing kernel profiling output. So overall, it performs better, the higher occupancy, and also if you look at the global load throughput, it's higher, and it can be optimized for this particular kernel. But still, we are 1.9 faster than non-fused version because we are running the 4 times. We are running this kind of kernel 4 times. That means we need to pay the 4 times of the more higher memory traffics. So this is the summary of the batched BLAS and LIPACK. We want to provide the user composable batched interface. So you can use this the functor level BLAS and LIPACK interface as your building block. And you can compose this batch BLAS and LIPACK by combining the parallel execution policy and then functor level interface. The performance on the GPU is the tunable. It means you can really mess up, or you can really make it very well. So launching the lightweight multiple kernels can cause some overhead, launching overhead, or some latency. And then we have the bandwidth problem here. But using too many kernels makes it difficult to make it optimize using selecting this team size. So you need to provide some right granularity of the decompose of your routine. I don't want you guys kind of include kind of 100 functor level interface in a single parallel flow. It's not going to work very well. So you need to kind of group certain functionality and stage, and you kind of put same parallel kernels. I mean the functor level kernel, they can perform in a similar fashion. In the BLAS, we have the level 1, level 2, level 3. They have the different level of parallelism. You can group them together and then put it in the single parallel flow, and then you get the better result. This is done. And next, Luke is going to talk about the sparse linear algebra.
Okay, I hope you can hear me now. I'm muting. So I'm Luc. I'm going to talk to you now about the sparse linear algebra component of Kokkos kernels. So here are the key takeaway and learning points for this section. So first I'll cover some key characteristic of the algorithms and the sparse linear algebra kernels that we're writing. Then I'm going to talk about some containers that are necessary for sparse linear algebra. Finally, I'll cover 3 typical kernels that are widely used in applications for sparse linear algebra, namely the sparse matrix vector multiplication, the sparse matrix addition, SPAD, and the sparse matrix multiplication, SPGEM. Okay, and so first of all, why do we need this type of package, like this type of sparse linear algebra? Well, the main reason for supporting these kernels is that they are quite important for a wide class of applications. So one such class of application would be applications that rely on the discretization of PDE system using discretization techniques such as finite element, finite volume, control volume, finite element, etc. Even some meshless techniques rely on representing their problem as a sparse matrix. And other type of applications that would also benefit from this type of representations are electrical grid model, electronic circuits, and social network graphs. And so to support this type of application, we decided to write the kernels using compressed row sparse format. The reason for that format is that it's fairly flexible, it's widely used, and so we fully support it in the sparse linear algebra of Kokkos kernels, and we also have partial support for block CRS format. So some constraints that come with the CRS format is that it's sometimes hard to optimize memory access pattern due to the sparse nature of the problem. You're going to have to fetch entries in matrices that are not necessarily matrices or vector that are not necessarily contiguous in memory, and that's just not the best way to access it, but it's a requirement for this type of format. We often have to write multipass algorithms. So for instance, SP-add and SP-gem are multipass algorithms, and the first pass you need to compute storage, and the second pass you'll need to compute column indices and actual values associated with the output matrix that you're trying to compute. And typically, because of these two passes, you can split the algorithm between a symbolic and a numeric phase. And so while this type of split is extremely useful, especially if you have reuse for part of the operation, it can sometimes be a bit slower than writing algorithm that will do all at once, but it's depending on implementation and other details. But still, symbolic and numeric split is what we would recommend. And if you think of finite element type of problems where you might have multiple time stepping and nonlinear iterations, during these iterations, you might be able to reuse the same symbolic phases. And so by symbolic, again, I mainly mean computing the CRS graph associated with a matrix. And I'm going to cover what the CRS graph is next. But before getting to that, I wanted to introduce the Kokkos kernels handle. And so what's the handle for? Well, one of the big points of our handle is to hide important details from the users to make things a bit easier, but that means you need to have a handle around. And so what does the handle do for you? So it stores user parameters. So it allows you to tune the behavior of the algorithms that we've written, the behavior of the kernels, while not having to have a cluttered interface for the kernel itself. It keeps temporary data needed in numeric phases or solve phases or applied phases of the kernels you're using. So if you're going to use a handle for the symbolic phase, it's important that you keep the same handle when you pass it to the numeric phase, and it's potentially also important if you're going to do some solve and apply for sparse solvers later on. The handle is also cleaning up and so taking care of this temporary data. It contains typically what I would call the subhandle that needs to be created, and subhandle that is specific to the kernel you're going to call. So typically, if you want to call a SP-gem kernel, you're going to have to create this Kokkos kernels handle and then create a subhandle that's a method of the main handle. And finally, this handle also specifies required data types for your algorithms to work correctly. So you can specify that the matrices have to contain doubles or floats or complex types, etc. Okay, so now I'm going to talk a little bit about the containers or the type of data structures that we use for sparse linear algebra. So typically we have one dense structure, and it's representing vectors or multi-vector, and that structure is just a view of rank 1 in the case of vectors and a view of rank 2 in the case of multi-vector. And again, when I talk about vector or multi-vector, this is a concept, like the actual data structure you use in your codes are views of rank 1 or 2. And then we have two sparse structures, the static CRS graph, which encodes the sparsity pattern in row map and entries. So row map and entries are two Kokkos views that are stored by the static CRS graph. And finally, we have a CRS matrix, which contains the static CRS graph, which is the sparsity pattern, and values associated with each entries in your matrix. And so for a bit more examples, you can go to the example wiki Sparse, Kokkos Sparse wiki CRS matrix.cpp. That's something we have in our source code. So currently we support two types of interface for SPAD and SPGEM kernels. One interface type I will call simplified interface, and it's useful for it's useful when you're having high-level containers in your code. So, for example, if you want to do SPAD, you're probably going to have output matrix and two input matrix that you need to add, and then the simplified interface just makes it easier for you to pass all that data in the kernel. It's also, it also reduces the number of parameters and templates you need to use, and it manages the allocation of memory for the output matrix automatically. So it makes life a bit easier. On the other end, if you care about finer granularity of memory management, if for some reason you're using an output matrix that already had its memory allocated, you might want to use what I would call the more expert or the more complex interface that relies on low-level containers, by which I mean the views that are contained inside the CRS matrix. And so the idea here is going to be to talk about, for clarity, the simplified interface for the rest of the lecture, since it's a bit simpler to look at and understand. Okay, so now I'm going to cover the three sparse kernels for today. The first one is the SPMV kernel, which is kind of a mixed kernel in the sense that the inputs are sparse matrix and a dense vector, potentially two dense vectors actually, and the output is one of the two dense vectors. So the idea is to compute the operation y equal beta y plus alpha ax. And because the output is a dense vector, this algorithm can work in a single pass since it doesn't have to compute a CRS graph for the output. And it presents a good amount of exploitable parallelism. It's embarrassingly parallelizable, like actually most of the kernels I'm going to present today. So the usage for that kernel is, as you can see, you have to pass a mode, which will tell you if matrix A has to be multiplied directly or has to be taken transpose of during the multiplication. And then you have two coefficient alpha, beta, matrix A, and two vectors X and Y. Again, you can find an example of usage in our example wiki Sparse subfolder. Second kernel that I want to cover today, the sparse matrix addition. So here the idea is to compute an output matrix C, which is equal to alpha A plus beta B, given A and B two CRS matrices. So for this kernel, having sorted inputs for A and B, and what I mean by sorted inputs is that the rows of A and the rows of B are sorted by increasing column indices, will speed up the call to the kernel. And so we have mainly, this is due to the fact that we won't have to call the sorting kernels ourselves, either on CPU or GPU, and these kernels have overhead associated with them. So one way for you to get extra speed out of that kernel is to sort the rows of your matrices. Usage, again, so this kernel is split between a symbolic and numeric phase. And as you can see, for the symbolic phase, the first parameter is going to be a handle. And then you just give the three matrices you want, two inputs, one output, ABC. And finally, for the numerical phase, it's pretty much the same interface, but you also have to specify the alpha and beta parameters that are going to be used in the operation. And again, example is available in our source code. So finally, I'm going to talk about the SPGEM kernel, the sparse general matrix multiplication, computes the operation C equal A times B for given sparse matrices A and B. You can see an example. And so one of the difficulty of this kernel, very much like the SPAD kernel, is that the sparsity structure of C is not known in advance. And so we have, again, a two-phase implementation, and this allows to efficiently determine the sparsity pattern of C. So here are the two phases: a symbolic phase, Kokkos sparse SPGem symbolic, which requires a handle again, and then matrix A, transpose flag for A, matrix B, transpose flag for B, and C, the output matrices. And the goal of the symbolic phase is to compute the number of non-zero in each row of C, and that allows us to allocate memory for the entries view and the values view of matrix C. And in the numeric phase, which has a very similar interface to the symbolic phase, we actually compute the column indices and the values of the non-zeros entries of C. Again, you can find an example in our example wiki sparse subfolder. So I'm going to talk a little bit about the actual algorithm for SPGem. So our algorithm follows the classical Gustafson's algorithm, and the key details of our implementation is to exploit hierarchical parallelism. And so we have at the highest level teams that are assigned contiguous chunk of rows in A. So you can think of the A matrix and you just chop it into large chunks. Now for each chunk of row, you use threads to assign to individual rows of A, and eventually vector lanes are assigned to the non-zero of rows of B. And that's how we split the problem hierarchically. And so finally, another key detail of our implementation is our use of a thread scalable hash map accumulator implementation. And so this is used in both the symbolic and numeric phases. We support both sparse and dense accumulators. It has a two-level structure, level 1 and level 2. The L1 hash map lives in our fast shared memory, which allows for rapid access to data. And L2 hash map is created only if we run out of L1. And so eventually the L2 then lives in the global memory. And so for more details on this algorithm, its implementation, I recommend the paper by Mehmet Deveshi. Okay, and that's what I wanted to talk about for sparse linear algebra. So I'm going to summarize my section. So the main difficulties of sparse linear algebra kernels are finding sparsity patterns and memory accesses related to sparse data structures. And the containers we use to implement and support the sparse linear algebra are views, static CRS graph, and CRS matrices. And finally, the kernels themselves that I presented, the sparse matrix vector multiplication, SPAD, and SPGem operations. All right, and now we're going to move on to the next section, which is going to cover graph kernels.
Okay, hi, I'm Brian Kelly, and I'm going to talk about the graph coloring kernels that we have in Kokkos kernels, as well as the Gauss-Seidel preconditioners, which are one of the primary applications of distance 1 graph coloring currently. So the first coloring kernel that I'll talk about is distance 1, which is just a standard situation where each vertex needs to have a different color than all of its neighbors. And this is a well-known NP hard, and actually, to be more precise, NP complete problem. But an approximate solution that might not be an optimal number of colors is still useful because vertices of the same color will be independent. And Kokkos kernels has two greedy algorithms for this problem, vertex-based and edge-based. So in vertex-based coloring, it's really a parallelization of what you might write as a simple sequential algorithm. So in parallel over each vertex, you loop over to the neighbors of V and find out what the smallest color is that isn't shared by any neighbor. And then you just color V with that. But since we're doing this in parallel, there can be data races where vertices might be adjacent and they end up with the same color. So we have to do a second pass where we find out where these conflicts happen. And then we uncolor the vertices that are in conflict and then add them to the next work list. And we just repeat this until all the vertices have been colored. Now, on the other hand, edge-based coloring is a parallel loop over the number of edges in the graph. And so basically you look at the two endpoints of each edge, and if they have the same color, then you uncolor the one with a higher ID as a tie break. And then if at least one endpoint is uncolored, you'll still need to work on that edge, so you add it to the future work list. And in the next pass, you propagate the allowable colors from the colored endpoint to the non-colored endpoint of each edge. And finally, you choose colors for vertices. And you just repeat these steps until the edge work list is empty. And that means that both endpoints of every edge have been colored with distinct colors. So to summarize these algorithms, well, yeah, I should say EB, the edge-based pseudocode, was simplified. There are some more sophisticated techniques that we use, like tentative coloring. And you can read about that in the 2016 paper by Mehmet and Siva and Eric Bowman about how that was done. But yeah, in vertex-based coloring, the work that each thread does is a loop over the neighbors of each vertex. And this can be arbitrarily high because a vertex can have a high degree in some cases. But in edge-based coloring, the work per thread is constant time because an edge always has exactly 2 endpoints. But the downside is that the work lists are longer, and so there's more overhead for managing that. So in general, edge-based is faster on GPUs when the maximum degree of any vertex is greater than 3,000 or so. That's a good rule of thumb. Otherwise, VB-bit is the recommended algorithm. So that's VB that uses bitwise operations to deal with tracking which colors are allowed for each vertex. So to use this algorithm, or one of the two algorithms, you use the Kokkos kernels handle that Luke talked about, and you create a graph coloring subhandle, and that's when you choose the algorithm to use. So in this case, we're looking at VB without the bitwise operations, just as an example. And you call graph color to compute the coloring. And here you're passing in row map and entries, which is the CRS graph structure. And then you can get the subhandle out of the main handle, that's called color handle here, and use that to where you get the number of colors that were used and the vertex color labels out of that. And finally, you have to destroy the subhandle to clean up any temporary memory that was allocated for that. And so now moving on to distance 2 graph coloring, it's the same idea, except of any 2 vertices within 2 hops of each other must have different colors. So this is equivalent to actually computing a distance 1 coloring on G squared if you're looking at the adjacency matrix of the graph. And the graph must be undirected. This is actually true for distance 1 as well, but the graph needs to be represented by a symmetric adjacency matrix. So for this little example, vertex 0 would need to have a different color than both vertex 1 and vertex 2 because those are within 2 hops of it. But 0 and 3 or 0 and 4 might have the same color because they're 3 hops apart. And then we also support a closely related variant of distance 2 coloring called bipartite graph partial coloring. And what this does is it looks at a bipartite graph and colors one side of it, either the left or the right, so that vertices 2 hops apart have different colors. And left-sided bipartite partial coloring is equivalent to doing a distance 1 coloring on G transpose, because the rows of the adjacency matrix that you pass in represent the left side vertices, and the columns of the matrix represent the right side vertices. And so because of this, right-sided bipartite coloring is equivalent to a distance 1 coloring on the transpose of that, which is G transpose G. And in this example, vertex 1 could not have the same color as vertex 0 because it's connected through vertex 4. But vertex 1 and 2 could have the same color because they are not connected by any path of 2 length. And then vertices 3, 4, and 5 all need to have different colors because they're all connected through vertex 0. And the two algorithms that we support for these problems are vertex-based, which is exactly the same as the distance 1 vertex-based, except that instead of just looking over direct neighbors, it has to loop over the neighbors of neighbors. So it's a nested loop. And this can get pretty expensive on GPUs especially. And on the other hand, we have net-based coloring, which is from this paper called Greed is Good, Parallel Algorithms for BGPC. And this is asymptotically faster than vertex-based because it only uses direct neighbor loops. So it's faster by a factor of the average degree, which is a huge speed up, and it's pretty much always faster in practice. So to use distance 2 coloring, it's very similar to distance 1. You create a distance 2 subhandle and select the algorithm. And here we're using the recommended NB bit. And then you compute the coloring. And finally, you can get the subhandle out and then request the number of colors used and the vertex labels, or of colors, and then clean up at the end. And to use bipartite partial coloring, it's the same kind of handle, except you just call bipartite color rows for left-sided coloring, or bipartite color columns for right-sided coloring. And we have an exercise for this in Kokkos Kernels / graph coloring, where you will compute both distance 1 and distance 2 colorings for a graph, which is a 9-point stencil on a small 2D grid. And a 9-point stencil just means that each vertex is adjacent to the 8 vertices around it in a square. And you can see the colors that it computed because it'll print them out in the grid layout. So to summarize our graph algorithms so far, we have distance 1 coloring, where adjacent vertices have different colors, but we're trying to minimize the number of colors used. And we have the vertex-based and edge-based algorithms. And as a rule of thumb, you should use BB-bit for any graph unless the maximum degree is very large, say larger than 3000, and then you should use EB. For distance 2 and bipartite graph coloring, we recommend you use net-based algorithm for pretty much any situation. So now moving on to our Gauss-Seidel preconditioners. We have multicolor Gauss-Seidel, cluster coloring Gauss-Seidel, and two-stage Gauss-Seidel. So here's a way to formulate the classical Gauss-Seidel method, which just kind of uses forward substitution to update each entry of the unknown vector one at a time. So for each row, you compute the residual, which is the quantity in the parentheses, and then you divide by the diagonal. And so you take that value and you put it into the X vector, and then that value will get used in all future rows in the same sweep. And because of that, this is an inherently sequential algorithm because updates will be used later on other rows. But if you look at the formula, the coefficient on xj is aij. And so this actually is usually 0. It's 0 for most entries if A is sparse, which means that if that aij is 0, then xj does not actually affect the updated value of xi. And this is true if and only if the vertices I and j are independent, which means they're more than one edge away from each other. And so we can compute a graph coloring of A and then update x sub I in parallel for any I of the same color. And that's what multicolor Gauss-Seidel does, is it's a way to parallelize Gauss-Seidel. So to use this, we create a handle. We create the sub-handle for Gauss-Seidel. And here we're choosing GS point, which is the algorithm enum value for multicolor. And we have a separate symbolic and numeric setup. So symbolic does the bulk of the work because it does the coloring of A. And so you can reuse that if just the values of A were to change in the future. And graph is symmetric, just means whether or not A's adjacency, well, whether A is structurally symmetric. Because if it's not, it needs to be symmetrized in order to run the coloring on it. And then, yeah, numeric setup. And to use the preconditioner to solve a system, we have forward sweep, Gauss-Seidel apply, backward sweep, and symmetric. And these all take exactly the same arguments. They take the handle, the dimensions, the matrix, including values, the X, which is the unknown, the B, which is the right-hand side. And then I'll explain these other parameters next. So init 0x is whether to zero out X before beginning. And so you might want to do that if this is the very first preconditioner apply in the system. And then update cached B is whether or not to recognize that B has changed since the last apply, or if it's just the first time applying on this system. And that's because some of these algorithms, like multicolor, will internally store a permuted version of B to speed up memory accesses. And then omega is the damping factor for successive over-relaxation. So you can put in anything for that. And of course, the default is 1.0. And the number of sweeps is how many times to apply. And for symmetric, the forward and backward counts as just one. So cluster Gauss-Seidel is a slightly enhanced version of multicolor Gauss-Seidel, where we use coloring on a coarsened version of the graph. And the reason for that is that even if rows I and J are independent, you still don't get exactly the same answer in multicolor Gauss-Seidel as you would in sequential Gauss-Seidel, because updates to X sub I might affect, say, X sub K, and then X sub K might affect X sub J. And even though I and J are independent, the order in which you process these three vertices actually does affect the answer. And so in practice, multicolor Gauss-Seidel gives a slightly worse preconditioner result than sequential. On average, it depends on the natural ordering of the matrix and everything, but so cluster Gauss-Seidel is designed to kind of alleviate this by coarsening. And then it applies sequentially within a cluster. So the clusters are independent, and then we're applying over each row one at a time within a cluster. So to use this algorithm, it's just creating a different algorithm in the subhandle. And it's an overload, so it takes the clustering algorithm or coarsening algorithm. Right now there's only cluster balloon, but more will be added in the future. And then the coarsening factor, cluster size. And so this is like how many vertices will be put into each cluster. And then the rest of the usage is exactly the same as multicolor. And then two-stage Gauss-Seidel is quite a bit different. It's some new work that came out of NREL and the ExoWind project. And so it's a hybrid between the Gauss-Seidel and Jacobi methods. So they formulate Gauss-Seidel as a lower or upper triangular solve, depending on which direction the sweeps are in. And then it uses Jacobi sweeps to approximate this triangular solve. And so, yeah, you just use the two-stage enum, and everything else is the same. And it doesn't use any coloring or anything. It just uses this, hybrid preconditioner. And there's an exercise for this too. It's in Kokkos Kernels / Gauss-Seidel. And it generates a small diagonally dominant system, which means that Gauss-Seidel can actually be used as a direct iterative solver. So there's no CG or GRES or anything. It just will solve the system by applying the GS preconditioner you create over and over until tolerance is reached in the residual. So to summarize the Gauss-Seidel algorithms we have, there's multicolor Gauss-Seidel, which uses distance 1 graph coloring to find independent rows and then applies on them in parallel. Cluster Gauss-Seidel, which is the same, but it colors a coarsened graph. And then two-stage, which is a hybrid between Gauss-Seidel and Jacobi or Jacobi-Richardson. And there's really no rule of thumb on which is the best. It really depends on your problem. But these are all supported in FPAC2 in Trilinos. So yeah, you can try those out with FPAC2. And yeah, so that's all I have.
I'm Nathan. I'm going to cover the next sparse section. We're going to cover 2 more sparse capabilities in Kokkos kernels that can be used for preconditioning matrices and sparse solvers. Our sparse incomplete LU factorization and sparse triangular solvers. The sparse ILUK routine computes sparse lower and upper triangular matrices where the product approximates the input matrix. It supports k-level fill, where k equals 0 is likely the most common use case. This case introduces no additional fill-in compared to the input matrix. For k larger than 0, more fill-in occurs in the L and U matrices, reducing sparsity. This helps to improve accuracy of the factorized representation of the matrix. The sparse triangular solver can be used as a follow-on step to sparse ILUK to essentially apply the matrix inverse to a vector by calling the solver twice, using the L and U triangular matrices from the sparse ILUK routine. Since the LU factorization only needs to occur once per matrix, it can be reused when applying the matrix inverse as a preconditioner at each step in an iterative solver. So we'll now go on to some details of usage of the routines. So the SPI LUK routine supports matrix data stored in compressed sparse row or CRS format discussed earlier. It consists of 2 phases. The symbolic phase, which analyzes the matrix structure on the host and determines the non-zero patterns for L and U. It performs level scheduling to group row indices together in a level of rows that can be computed on independently during factorization, and where the levels are ordered by dependency. This is done to expose parallelism for the next phase, and the results are stored in internal data structures in a handle. The second step is the numeric phase, which performs the factorization in parallel using the level scheduling results from the handle and fills in the data arrays for L and U. The results of the symbolic analysis can be reused with new matrices if the non-zero structure does not change. And there are 2 algorithmic options. One that implements the numeric factorization phase using Kokkos range policy and flat parallelism. The other implemented using hierarchical parallelism with Kokkos Team policy. The second option is likely the best performing in most cases as it exposes more parallelism in the algorithm. The interface requires the CRS arrays as rank 1 views storing the row map, the entries or column indices, and the values for each of the A, L, and U matrices, A being the input matrix. It also requires an opaque handle object that was discussed in the previous sparse section, which stores internal data structures and parameters to support the routine. When initialized for sparse ILUK, the handle takes arguments for the algorithm option, the number of rows of A, and estimates for the number of non-zeros of L and U. So now we'll go over some code snips to demonstrate the actual usage. So include the header file. This is a relatively new routine. It exists in the experimental namespace, meaning that the public interface may undergo further changes. For convenience, we add this using statement just to turn down verbosity in the remaining lines. So next, create the opaque handle, and then initialize the handle for sparse ILUK. So pass arguments for the algorithm option, the number of rows of matrix A, and estimates for the number of non-zeros in L and U. Users are required to provide the estimates. Then call the symbolic routine. and a numeric routine, which completes the factorization of the matrix. The sparse TRSV, or triangular solve routine, supports the same CRS arrays as the sparse ILUK routine, and it consists of two different algorithm implementations that have different interfaces. There's a level scheduling based implementation that I'll refer to as the fallback implementation, and a supernode based implementation. The fallback implementation consists of two phases: the symbolic phase, which analyzes the matrix structure on the host and performs level scheduling to group row indices together in a level of rows. And these are rows that can be computed on independently during the solve, with, again, the levels being ordered by dependency, similar to SPILUK. The results of this are stored in internal data structures in a handle. There's another optional feature that can be used to attempt to reduce kernel launch overhead in GPU runs for cases where there's levels with too few rows and the solve is dominated by kernel launch time. I'll talk a little bit about that on the next slide. The solve phase completes the solution of the triangular linear system using the level scheduling data from the handle. And again, the results of the symbolic analysis can be reused with new matrices if the non-zero structure does not change. So there's three different algorithm variants that you could try. The first performs level scheduling on the host and uses Kokkos hierarchical parallelism within the solve phase. The second is a variant of the first and can be useful in GPU runs. It allows a chaining of consecutive levels together that have too few rows, or that have few rows, and in these cases where the solve is dominated by the kernel launch overhead. So in this case, a single kernel launch for all those levels can help reduce the kernel launch overhead to hopefully improve performance. And this can be useful, for example, with banded matrices. And if you have Sparse enabled, there is TPL support for the Sparse implementation of the triangular solve, which performs well for GPU runs. Like the sparse ILUK, the interface requires the CRS arrays as rank 1 views for the row map, the entries, and the values. It also requires the opaque handle. And when initialized for SPTRSV, it requires arguments for the algorithm choice, the number of rows of A, and a Boolean that will indicate whether the matrix is lower triangular. And it's true if it's lower triangular, false for upper triangular. The solve phase also requires rank 1 views for the left and right hand side vectors of the solve. So going back over, or going through some code snips here of usage, include the header file. And again, this routine is also in the experimental namespace. So we include the using statement for reducing verbosity, create your opaque handle, initialize the handle for SPTRSV, and the lower and upper triangular matrices will require separate handles. Call the symbolic analysis, and then call the solve routine. The supernode-based sparse TRSV routine requires users apply reordering and factorization to the matrix and to also provide supernode block information to the routine. Metis and SuperLU, for example, were used during the development of this algorithm. It consists of three phases: a symbolic phase, which performs level set scheduling of dependencies among the supernode blocks, and it saves the info in the handle along with preparing internal data structures to store matrix blocks on the GPU. There is a merge option to merge supernodes with the same sparsity structure before level scheduling, which can help performance in some cases. There's a compute phase, which copies the matrix values into the handle's internal data structures. And there are options available to invert diagonal blocks and also to apply the inversion to off-diagonal blocks. Then there's the solve phase, which uses the level scheduling info to complete the solve and exploits the available parallelism in the algorithm. So there's several variants for algorithm choices. There's supernodal DAG, which applies Kokkos kernels batch TRSV or GMV kernels to supernodes at each level, and internally it computes the DAG for scheduling. There's supernodal SPMV DAG, which applies sparse matrix vector multiplication at each level and requires inversion of the diagonal blocks, and optionally applying inversion to the off-diagonal blocks as well. Internally, this computes the DAG for scheduling. There's supernodal E-tree, This is very much like the supernodal DAG method, where scheduling is based on a user-provided E-tree, which, for example, can come from SuperLU or CholMod. And supernodal SPMV, which is like the supernodal SPMV DAG version, where scheduling, again, is based on the user-provided E-tree. For more details in these algorithms, I refer you to the paper listed below with the link there. Now, the solver requires the row map and entries be passed together as a static CRS graph for each of the L and the U matrices, requires the number of supernodes, an array containing the size of supernode blocks, an optional E-tree that can be used for level set scheduling, and an opaque handle, like previously discussed. And the solve phase also requires the rank 1 views for the left and right hand side vectors. So a brief walkthrough of usage of the code. Include the header file, and create your opaque handle, and initialize it for SPTRSV. In this case, we're going to demonstrate using the supernodal SPMV DAG algorithm option. And then set options. For example, if you want to merge supernodes, by default, this will be false. To invert the diagonal blocks, this is required for the supernodal SPMV DAG routine, and whether to apply diagonal inversion to the off diagonal blocks. Then call symbolic analysis, call the compute phase, and finally call the solve phase. So as an exercise and a use case, we have a preconditioned conjugate gradient example. The exercise begins with an implementation already in place of the conjugate gradient algorithm to solve a linear system, in this case using a simple Laplacian matrix on a Cartesian grid. And the goal is to introduce changes to the code necessary for preconditioning, which are marked by green boxes in the algorithm box on the right. This will entail introducing code to apply the sparse ILUK routine to A to attain the triangular L and U matrices. Their product is represented by the matrix symbol M and going to be used as the preconditioner. Then you apply two triangular solves using SPTRSV to the residual R in order to compute Z for each iteration of the solve. The exercise is located in the directory specified here, this Kokkos kernels CG solve SPILUK precon. And there's already been some prep work done in the source code. There's a convenience script for all these exercises that will install the Kokkos kernels library and also generate make files for the exercises. That's called run install lib cmake.sh. You may need to change some of the options for your particular setup. For example, make sure that you're pointing the Kokkos path to your Kokkos source directory, similarly for the Kokkos kernels directory, and also enabling your the execution spaces through the Kokkos devices variable there that you want to configure for. So in the CPP file, look for lines that are marked by the exercise keyword. This will guide you on the steps to follow. There's some pretty heavy-handed hints that can help that are marked by the exercise hint. And you can ignore those, of course, if you want to give this a try without any extra help. The key steps will include initializing the SPTRSV handles, calling SPILUK symbolic and numeric routines in the appropriate places, SPTRSV symbolic phase, and then calling SPTRSV solve twice each iteration of the solver. Once complete with the code and getting that compiling, you can test with different command line options to see how convergent rates are affected with and without preconditioning and by changing the fill level of ILUK. If you run the executable with a -- help, that'll show you the command line options for controlling this. Okay, so that completes this section on sparse solvers. Now we're going to move on to CMake. This is the final section. We'll discuss the build system, including using Kokkos kernels with your project and how to configure and install. Your options for building with Kokkos kernels include installing with CMake. This is the best for large projects with lots of dependencies. You can build inline, which is an option when you have applications that have few dependencies. And if you're already using SPAC for components of your code, then SPAC is also an option for installing Kokkos kernels. With the 3.0 release, Kokkos and Kokkos kernels adopted CMake as the build system, adopting modern CMake practices aimed towards build system portability. The goal is to keep things simple, meaning a single build system call in your project should configure all compiler and linker flags. When configuring Kokkos kernels, most settings come automatically from Kokkos, and there should be no need to link to Kokkos itself, as Kokkos kernels transitively applies all Kokkos flags. Proper handling of transitive dependencies is important. For example, in an application that may use Kokkos indirectly, with Kokkos details hidden behind layers of abstraction, flags need to propagate to the application to allow this, and CMake helps make this nearly seamless. We'll cover briefly 3 scenarios using Kokkos kernels in your project with CMake. In this first case, if you have an executable and an installed Kokkos library, you create your CMake list txt file, declaring your C++ project. Then find Kokkos kernels and fail at configuration if it's not found. Add your program, and then link non-transitively to Kokkos kernels using the private keyword. In the second example, if you're using Kokkos kernels as a submodule, you create your CMake list txt file and declare your C++ project. Add Kokkos and Kokkos kernels subdirectories. Add your program. Then link to Kokkos kernels using public keyword in this case. In this last scenario, for libraries using an install of Kokkos kernels, create your CMake list txt file declaring your C++ project. Find Kokkos kernels, and again, fail at configuration if it's not found. Add your library, then link to Kokkos kernels. In this case, to make sure that the Kokkos flags propagate properly to downstream apps, make sure to use the public keyword for transitive dependency. And here we're going to show just a minimal CMake line that you would use for configuring Kokkos kernels. This will include pointing to your source code, making sure to set the compiler to use the same compiler that Kokkos was used with, pointing to your Kokkos kernels install, and then setting desired Kokkos kernels options. Those options fall mostly into 2 categories, with ETI options available to pre-generate kernels of various types in order to reduce compilation overheads. And this includes options such as the scalar type, ordinal and offset type, execution and memory space, and layouts. For subroutines, third-party library support is available and can be enabled giving access to vendor-optimized options like Intel's MKL, NVIDIA's cuBLAS, and cuSparse. So here's a couple of concrete examples showing how to enable options in Kokkos kernels. These first 2 setting options are of the ETI category and show how to pre-instantiate kernels. In the first case with CUDA UVM as the memory space, and in the second case, pre-instantiating kernels for 32-bit floats. The last 2 options shown here are from the TPL category and show how to enable MKL and, on the last case, SuperLU, as well as how to point to your local SuperLU installation. During configuration, you'll get a summary of activated options output to the screen, showing enabled ETI types, and then a list of enabled TPLs after that. Now, SPAC provides a package manager that supports installs of Kokkos and Kokkos kernels. Specific compiler and variant combinations are supported and can be called from the command line as shown here for an install of Kokkos kernels with the develop branch, with OpenMP enabled and using GCC as the compiler. You can run SPAC info Kokkos kernels to see a full list of variants that are available. You can create build rules in SPAC package files, which require declaring a dependency on the specific version of Kokkos kernels, adding build rules to point to the SPAC installed version of Kokkos that should be present, and the same compiler that Kokkos was built with, just like if you were doing this with CMake. And more details about SPAC usage can be found in the SPAC markdown file in the Kokkos repo. Okay, this completes the build system section of the tutorial. And with that, that completes the end of the Kokkos lecture. So in summary, a couple points we want to leave you with is that Kokkos kernels provide several performance portable, dense, sparse, and graph kernels. The team actively works with vendors to incorporate algorithms in optimized vendor libraries and provide interfaces to them. The Kokkos core, Kokkos kernels, and Kokkos tools allow the Kokkos ecosystem to be a complete solution for computer science and engineering applications. The team works actively with applications to address unique use cases, and please reach out to us either through Slack, GitHub, or email for further questions. And with that, I turn this back over to Christian Trott.
So this is the end, at least the end of the Kokkos lectures, which we've done over the last 2 months. We had 8 lectures, a total of over 600 slides, 14 hours of recording as soon as this thing is going up. And I hope you all enjoyed that and found that very informative. We talked about most of everything in the Kokkos ecosystem, right? We talked about obviously the Kokkos core, parallel execution and data structures, etc. We talked about the PGAS system. We didn't talk about the resilience, which is a new thing which is coming out, and we'll probably share some stuff on that in the coming month or so. We definitely talked about Kokkos tools, and today about Kokkos kernels. And I hope what you got away from this is that Kokkos is a mature solution for writing performance portable code. It's something which has a lot of support across the DOE laboratories, and it's something you can reasonably well rely on. What did we cover? We cover kind of everything, more or less everything in the code which you need to write Kokkos codes. We talked about how to build Kokkos and your applications. We talked about how to do parallel execution. We talked about data management and how to manage heterogeneous architectures. We talked about more complex data structures and multidimensional loops. We talked about hierarchical parallelism. We talked about tasking and how interoperation with things like CUDA streams work, or generally the asynchronous system or the asynchronous properties of the Kokkos programming model. We talked about SIMD vectorization. We talked about Python and Fortran interoperability of Kokkos. We talked about how to mix Kokkos with MPI. And we talked about something we believe will be in the future useful, the integration of PGAS, or partitioned global address spaces, into Kokkos, and how global arrays kind of syntax will allow you to write more simple code. We talked about tools, how to do profiling and tuning and debugging of Kokkos code, and about the math kernels. All of this is obviously the work of not just a few people. There was a huge team involved in, there's a huge team involved in the whole Kokkos ecosystem. We have people at various labs who are, core contributors to the entire endeavor. And obviously we have, people who were here before and are not, and left us in the meantime. In particular, I want to thank Carter Edwards, who started, this kind of incarnation of Kokkos back about, almost 10 years ago. I want to thank Mike Carew, for believing in this project, and in particular in its early phase being a real good champion for us, who allowed us to pollute, Trillinos with Kokkos and demonstrate that this actually can work. One other person I want to specifically thank is Jeff Emling, who actually developed the original tutorial material in 2015. And about 100 of the 600 slides or so, which you saw during these lectures, are actually stuff he developed back in 2015, which is both a good sign for how stable the Kokkos API has been, that we can still use that training material, and for what kind of good foundation he laid for developing our training material. Then I want to thank the Sandia LDRD program, which did the initial funding of this Kokkos effort, and obviously the DOE Exascale Computing project, which has been funding for the last few years, in particular our training efforts, and then our expansion of the Kokkos team to the other labs so that we can give you better support at the different HPC centers. And with that, welcome to Kokkos. Welcome to the Kokkos family. If you really made it through the 14 or 15 hours or so of recordings here or lectures, you are now officially a Kokkos developer, I would say. And we hope that helped you to get started. You find us on GitHub. You hopefully joined the Kokkos Team Slack channel already and can ask us questions there. And we'll hope to hear from you and what your experience is with Kokkos. And we hope you have success in your performance portability endeavors. And with that, we are done. See you all.